Hello, everybody, and welcome to Setting Up Kernel Debugging and More, a poster walkthrough with Jonathan Ryder. We ask that you please send any questions you have during this presentation through Zoom's Q&A feature located at the bottom of your screen, and that you keep an eye on the chat for helpful links and additional information as we go. Thank you all so much for joining us today, and without further ado, here's Jonathan to get us started.
Hey, thanks for the intro. Welcome everybody to my poster walkthrough. Obviously, we're gonna have two sides to this. The first side of this poster is dedicated to basically setting up kernel debugging and how to get started with that, and how to start doing things like process enumeration from a kernel perspective, how to break into the context of a user mode process, looking at breakpoints, looking at functions, finding functions with wildcards, and stuff like that. So that's going to be like the first portion of this walkthrough. And then after that, hopefully you have the poster downloaded so you can kind of walk through-ish with me. I don't expect you to have a VM or anything like that set up. That's totally fine. I'd rather you just kind of go along with me with a poster that you have downloaded locally on your side. All right, so one side is dedicated to all the debugging things. And then on the flip side, we have a bunch of stuff kind of smashed together. But kind of front and center is some like Windows developer knowledge. Some of the stuff that I would say isn't very well known for like implant developers or malware developers or whatever you would like to call yourself. And that is being able to use intrinsic functions. And I'll talk about intrinsic functions in just a little bit more detail when we get to this section. And then also down towards the bottom of this section page, I'm not really going to dive into much of any of these because we only have an hour here. But given like a very high level overview of function hooking, what syscall stubs kind of look like, what a hooked system call stub looks like, so on and so forth, and then some general terminology. What is position independent code? What are position independent functions? And then diving deeper into some very useful intrinsic functions that maybe you've seen before, maybe you've used them before, to help you do things like find the pointer to the PEB, and to start going through doing like a PEB walk. Okay, so something that's very important for shellcode authors and even implant developers to know how to do, and is to go through and do a PEB walk. All right, so welcome everybody. I see a few more people jumping in. Awesome, thanks for jumping in. This is going to be recorded, so if anytime you want to go back and re-watch this, you absolutely can. And also, if you're not in the SANS Offensive Ops Discord server, a little plug for that server, that's a great spot to be. There are some dedicated channels for a lot of the Offensive Ops classes, and also there's a channel for workshops. I do a lot of workshops for SANS. They're free and they're all recorded. One of the ones I just did was Intro to C for Windows. And then I also just started a new series for Intro to WinDebug, okay, which is perfect with this poster. This poster will have a little bit of focus of the kernel mode, but what's very valuable of this is knowing how to do debugging, especially as you're going through the motions, trying to dive into malware or implants or whatever, just a little bit deeper with the operating system, understanding internals and stuff like that. It's very, very valuable to have a skill set of debugging. All right, so cool. So what I'm gonna do is we're gonna go through this first few steps to basically show you all how you can get started setting up kernel debugging from one VM to another VM. Call this remote kernel debugging. There is such a thing as doing local kernel debugging. Now, I really don't recommend doing local kernel debugging, or LKD, a lot. There are some things that you just can't do with it. And in my opinion, the full-blown remote kernel debugging is far more powerful. All right, sweet. So one of the things that you need to go ahead and get started with remote kernel debugging, you need two systems. Okay, they can be VMs, they can be actual hosts, physical hosts, whatever it is. Okay, so I have two VMs. I have a Windows 11 VM that I use as my debugger, and then we have a Windows 10 VM that is going to be the debuggee. Okay, this is one that we're going to get set up to go ahead and debug and explore in that sense. Okay, so step one, done. We got two systems. Step two, you need to have a couple of files that are present on the debuggee. Okay, what that means is KDNet and the verified NIC list. Okay, so those should be present from your debugger system when you have debugging tools and the SDK and stuff like that already installed. Those two files and many, many more will already be present. All you have to do is like drag and drop, copy and paste, or whatever, but get those two files over to the other system. Okay, so I have that already. So if you run KDNet, this is my preferred way to go ahead and set up a remote debugger connection and modify the settings. Okay, there's plenty of other utilities that allow you to do this. This is what is baked into the SDK and stuff like that. So this is what I like to use. Okay, you run it by itself and basically is doing a little check. Okay, and it's parsing the XML file, the verified NIC list, to go ahead and basically see if the NIC that your system has is supported for kernel debugging. Okay, specifically network kernel debugging. So we're good to go. So we can go ahead and specify a few more parameters here, but before I do that, let's go ahead and see what the question mark shows us, because maybe you've never run KDNet before and you don't know fully how to specify requirements for it. So the first two things that we need a host, the IP address or a name, and then of course we need a port. Okay, so you can see some other options are there as well, but I'm not going to mess around with those. We're going to do just the bare bones. Okay, so KDNet, and then I need the host IP, and let me grab that. And see if we can just copy and paste this over. There we go. And then we can specify a port. I recommend using like a pretty high ephemeral port, like 50,000. And go ahead and hit enter, and it does some things. Cool. And of note, it basically tells you what you can do on the other system, the debugger system. You could, at the command line, run this. You can do that. I'll show you how to manually plug and play and use those values inside of WinDebug or WinDBG here in just a second. It also tells you what to do next. It says go ahead and reboot this machine by running this. Okay, so you can go ahead and kind of prep that a little bit. We need to go ahead and take this key. So I'm going to grab all of this, put that in my clipboard, and now let's go ahead and open up WinDBG. Okay, cool. And to go ahead and get started with kernel debugging, if you just go to File, attach to kernel, and for the net, okay, this is going to be network debugging. The key here is saying, hey, what is the key that KDNet gave you? So just paste that in. And then the port, you can change the port, but it has to match, obviously, with whatever you used for KDNet. And you can see the target IP, not required. Okay, awesome. We hit OK, and what we see here is we're going to head and wait to go ahead and connect to the target. And we see we already have a connection, right? Connected to target, blah, 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 on port, blah. Okay, sweet. We didn't have to reboot. Now, that probably won't always be the case. You might have to do a reboot. Okay, so you go ahead, run that command to do a shutdown RT0, and when it comes back up and going through the whole boot process of being initialized and all that stuff, eventually at some point in time on the kernel side, the kernel debugger side, it'll go ahead and break. It'll pause the VM from doing anything more, and it'll give you full control to do whatever you want to do. All right, so now it tells us the debuggy is running. Yes, obviously it was running because I just went to that VM and I could do whatever I want with it. So what we can do is we can forcibly break that system from running anymore, because now at this point in time, we want to do things like maybe explore memory, maybe issue some commands and stuff like that. So I'll go ahead and hit break. Hey, there we are. Disassembly window is populated with some instructions. Memory has some junk in it. Everything is ready to rock and roll for us to do some stuff with the debuggy. Okay, so sweet. We're good to go. We attached to our kernel system remotely, and we got our connection established. Sweet. And feel free, if you have any questions, you don't have to wait until the end. Fire whenever you're ready. Go and send off your questions. All right. Cool. So one of the things that you can do as you explore the basic kernel debugging commands, you can look around here, and I kind of show you how to navigate your way around with some of the stuff. One of the things that I like to do just for my own workflow is to set up a log file. Okay, you can do a log file .log append and give it the full path to wherever you want your log file to go. So let me show you what that looks like. Tab completion also works pretty good inside of WinDebug. So .log append, and just give it the full path to something. I'll just put it on the desktop. We'll call it, I don't know, poster demo.log. Okay, there we go. And let's go ahead and just validate that it's actually there. Yep, cool. And it went ahead and it already gave us one entry, and that's this right here. Opened log file, whatever. So now anything that we do, any kind of commands that we put here in the command bar, will go ahead and be logged. And of course, all of the output from all the commands and stuff like that will also be logged, which is kind of nice. So whenever you're done with this and you want to look through something later, you want to do like a Control F or whatever to kind of look through things, post your debugging session, it's there. Okay, kind of cool. Okay, so the next step that we can do is we can start to explore the actual debugger session that might be set up. Okay, so we use a very fancy command, dx. It's a more modern version from a previous one called like dt. I still use dt a lot to display types and stuff like that. So dx, if you just tab complete, go ahead and say debugger. And one of the things you can do is do a dot and just tab complete around. Okay, and check out some sessions, the last debugger event or whatever. So right now, let's just check out some sessions. This should be our one and only debugger session, and it is. Okay, and also gives you the specifics about it, the port and the key that was used. So if for whatever reason you lost the key, forgot what it is, because on this side, you only see that key once. Okay, so you can save it off in a text file or whatever, but it will also be present for this current debugger session. And the key doesn't change too often, however, it can change. All right, so we take a look at the debugger sessions. We see there is one session present, so we can come after the sessions there and do a dot and see what's after this. You're going to take a look at all, any, some other things, account, and first. Okay, basically telling it to go ahead and give me more information about the first debugging session that it knows about. So you could go ahead and you can try to hit enter. And it's like, yo, I don't know what that is. I have no idea what .first is, meaning this is a method. Okay, so predicate method. So you go ahead and call it. Okay, you call the method, you invoke the function or whatever you want to say. And boom, there we are. So in this current debugger session, the first one, our only one, we have a couple things at our disposal. We could go ahead and click on processes. We could go ahead and click on OS, devices, attributes, whatever. So I can click on OS, and then there's the build string. Click on version 10, yeah, cool. And then more details for that, major, minor, build, stuff like that. Okay, when you click on this stuff, it will show you the commands that it executed behind the scenes, which is really cool. So you can see this dx command with attack R1 debugger sessions first.os. And the attack R1 is basically a recursive kind of level. So if there are any let me see if I can come up with my history here. Up arrow. Right there. And let's just play around with it and see what happens. Okay, so attack R3. We'll go ahead and go basically 3 levels deep from any nested structure or anything else that it finds. Okay, so that's kind of cool. Okay, that's definitely applicable for any other place where you might need to inspect certain structures from the kernel mode. You want to pull apart certain fields from them. You can choose the recursive level, if you will. All right, how deep do you want to go inside this structure? Because Windows loves using nested structures within nested structures within nested structures. It's very structure heavy. All right, so cool. We took a look at some basic information about the debugger session itself and some basic information about the target that we're actively connected to right now. Okay, sweet. So let's see what else we can do. All right, we can go ahead and start to look at all the processes. So let's go ahead and do that. You can come up here and just click on processes. All right, there we go. Cool, and gives you a nice little formatted listing of processes. And over here, basically we just have like a PID that's in hex. And you can click on them. As you see, they're all blue hyperlinks. And we have the process name, and that's about all the information that we have right here. Okay, which is fine, right? If you want to just do a basic high-level listing of all the processes, fine. And if you want to dive deeper into something, you can. And one of the other options that you see here is the ability to go ahead and switch to that process context. Here's the importance behind doing that. Right now, we are in the kernel context. Okay, we're in kernel land. We can do whatever we want, obviously, because we're kernel debugging. And let's say you're interested in the command prompt, the command process or whatever, like Notepad or anything, any kind of user mode process. You want to set a breakpoint in there. You want to inspect some memory or something like that in there. One of the things that you should do first is go ahead and switch to that user mode context to find things like modules that have been loaded inside of that process and other stuff like that. Okay, so you could go ahead and click on one of these switch tos. I want to show you real quick though, if you don't like seeing the hex display for the process IDs, after processes, if you just do a comma and then D, they'll go ahead and give you the decimal representation of that hex value, right? It's a lot, I don't know, for me, I just like that. It's a lot easier to read, especially if you happen to know a PID of interest or something like that. You can look for that specifically. All right, but most time we're looking at the actual name of a process. Okay, like the command prompt, all right? The command prompt is running on the other system, so you can go ahead and click on that, and you can see what it gave you, okay? The command that it ran behind the scenes. All right, so the DX are one, and then the dot processes. But instead of doing a high level listing of all processes, we basically are treating it like an array. An array that we use as an index, and the index into this array is a process ID. Okay, so it's kind of cool that way. Now we can see various things like the kernel object, the ID threads that might be present, loaded modules that might be there, environment variables, attributes, devices, IO, stuff like that. Okay, and then over here on the far right, it still gives us that ability to go ahead and try to switch to that process context. Okay, all right, so let me make sure I'm not getting ahead of the poster here. All right, cool. DML proc, that's what's coming up next. Okay, so if you go through the motions and you're like, let's go ahead and let's just do that. Okay, switch to. And it really doesn't give you anything else. How do you know if you actually switch to the context of that process or not? One of the things that you could do is take advantage of the DX command and use like a pseudo variable, if you will. Okay, a lot of times these pseudo variables, they'll start with like an $@ prefix and get the name of the variable. So DX $, cur process, basically mean current process. What is the current process that I'm in? And the name should be the name of the one you tried to switch to. Okay, you shouldn't see entos kernel.exe or anything like that. You should see command.exe, notepad.exe, or whatever you're trying to inspect. And same kind of things, you can check out threads, modules, or what have you. And one of the things that you could try to do is take a look at the PEB, right? The process environment block that would be unique to that particular process. And every once in a while, you won't be able to see everything inside of the PEB. Okay, sometimes you'll get something like this. Unable to read memory at address, whatever. And you might see that at a lot of places inside this. What that could possibly indicate is that the process environment block, either half of it, a portion of it, all of it, or whatever, has been paged out. And so you actually need to bring that back in. You need to page that back in so it can go ahead and process everything. Okay, a lot of times there can be some actual indicators for you by WinDebug that will indicate something might be paged out. Okay, so cool. So you can see that some of the stuff is clickable, right? You got the blue hyperlinks, okay? And you can go through the motions and start to click on some of these if any of these are of interest to you, okay? Now, it looks like we're inside the process, right? We can see the PEB for it, which is great. Every once in a while, though, the switch to just really fails, right? It doesn't really get you fully in the context of that process. A couple of years ago, the switch to really wouldn't do anything at all. And so you had to go back to like an old school method. Okay, so old school method, which is still present in this new version of WinDebug, is use the debugger markup language, DML _ proc. Right, now we have another process listing. And this gives us the address of the eProcess object for all of these images. Of course, we see the PIDs in hex. Okay, so if we're looking for a command prompt, come all the way down towards the bottom, and you can go ahead and click on that. Okay, so cool. We have a little bit more details, but not full details, so we can go ahead and click on that. Okay, sweet. So now we have a lot more information about this particular image. Okay, the image name, directory base, where the process environment block is located, the parent process, that's what the parent CID is. Okay, so that's a parent process. It's also clickable if you want to check that one out. How much time it's been in user space versus kernel space, virtual size, blah, 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 some other kind of stuff, and a little trace, if you will, of the stack. Okay. Sweet. Now to go ahead and use this method to get into the process, what you can do is you can click on select user mode state, and we'll go ahead and do that and see what happens here. Okay, going through the motions, trying to pull down symbols from Microsoft's symbol server. It says we're good. And yeah, implicit process is now this process, okay, which is, again, the address of the eProcess object for the command prompt. Every once in a while, it may or may not tell you to go ahead and let execution continue with like a G. All right, let it go. But it didn't show me that right here, so we're good to go. We don't have to do that. Okay, we could go ahead and just run the peb command again to go ahead and take a look at it. To make sure that we are indeed inside that process address space, because if we weren't, the peb would basically be empty if we were in the kernel context. Okay, so another way you could go ahead and check to make sure you're in there. All right, sweet. Current process. Yeah, missed that one here. So yes, there is a way to go ahead and use the dx command to filter all the processes and look for a particular name. Okay, so let's go ahead and flip back here. Check out the history. And where did I have that? Okay, there's a few ways to do this. Inside the poster, give you a very detailed way. And let's try this, a little shortcut, see what happens. Okay, just looking for MSP engine, Defender, see what happens. There we go. Okay, the other way, the whole flatten thing and all that jazz, that works too. But every once in a while, I like to take a shortcut where you can. So that way, this way works as well. Okay, so it gives you that information in the PID in hex and the whole switch to thing if you want to try to go ahead and get into that context of Defender. Okay, so that's what filtering could look like using the dx command. With the main DML proc, I don't know of an easy way, or rather any way, off the top of my head to do filtering based off of an image name or anything like that. If you happen to know that, please let me know. It's kind of cool. That would be really cool to have. All right, so cool, we're good there, good there. Okay, all right, sweet, and LM command. All right, so LM is a way to go ahead and just basically list modules, right? That's it. It's a listing of modules that have been loaded either in a kernel context or a user mode context. And one of the other things you can do is you can say LMU, to specify only show me the modules in user space, right? That's for the U. And then we have a couple of them here. The command, the image itself, in the symbol file for that. We have ntdll, and the symbol for that one. And you can click on any one of these, like kernel base. Okay, so kernel base, their symbols are deferred because it hasn't fetched them yet from the symbol server. It hasn't stored them locally on my system just yet, so we could go ahead and do that. And let's say, while we're in this process, let's say you're interested in a very specific function or whatever, but you really don't know the full name of that function. You just know it's inside of kernel base. That's it. And maybe you know it has the word create in it. So what you could do is you can do xfd, and then let me see, let me make sure I'm not looking at the wrong one. Okay. All right, so XFD is basically going to go ahead and search for all the functions inside of kernel base. And we know it has the word create in it at the beginning. So kernel base, bang, to go ahead and be our little separator or delimiter from the name of the module to the name of the symbol or the function. So create. All right, but create what? I don't know. I forget. Create something. So you can do create splat. And you go through the motions. Okay, so now it's pulling down symbols. And we have a ton of hits. Woohoo! A lot of create functions. Okay, all these create functions will basically need the help of the kernel to create an object. So let's see if I can pull one out here. Create an event. Okay, so create an event. All right, there'll be an event object that'll be created and stored in the kernel space. And then what's given back to you would be a handle to that object. And that's how you would interact with it. Okay, same thing with a process. A process object will be created, or a thread object to be created, and then the handle gets returned to you. Okay, so you can do a little bit more refinement on this. Okay, create proc. How many functions have create proc in the name? All right, quite a few. Create process internal, create process as user. There's an A version, okay, there's a W version. That's for ASCII versus Unicode. All right, the W is for Unicode, the A is for ASCII. Create process A, create process W, so on and so forth. Okay, so now that we kind of filtered out the noise of all the functions that are exported from kernel base, we could go ahead and decide to, maybe set up a breakpoint inside a command prompt, inside of kernel base for a particular function. Let's just say, let's just take the last one. Create process W. All right, so a double right click is basically a fancy little copy paste. And in front of this, we need to use the BP commands, right? So breakpoint, and boom, right? So breakpoint has been implemented. You could do a listing of breakpoints by using the BL command. All right, so list all the breakpoints. We have an option to disable it or clear it. When you disable a breakpoint, it's still there, but it won't actually be hit or triggered or anything like that, right? It's disabled, right? It's in a quiet mode. Clear, if you click on that one and run BL again, it basically says delete the thing, right? We don't care anymore about this particular function from this particular module inside a command prompt. Okay, who cares about it anymore? Okay, so that's how you could go ahead and set up a breakpoint inside a user mode space, right? Once we're inside the context of that process. Okay, all right, let's go back to the poster here. All right, yep, good. Show the LM command, XFD, breakpoints, peb, loader, and symbols and manifest files. Okay, so I'm not going to demo this. The reason why is just because they take a long time to run, right? There's no point to sit here and just watch these process. All right, so every once in a while, I have to work on a system that is air-gapped, meaning that system will not have any kind of access out to the internet whatsoever. So when it comes to symbols, and I'm remotely debugging that system, I won't have access to the symbol server to go and pull that stuff down. So what you can do is you can create something called a manifest file. All right, so generating a manifest file for offline system use. You can be specific and say, I'm only interested in the symbol for entosKernel.exe or notepad.exe or whatever. Okay, you could go ahead and be specific on that one particular piece. All right, so when you do symcheck and then /om, all right, to say, hey, I want to create a manifest file for whatever particular image. Now, to go ahead and ingest that manifest file, you take that manifest file, transfer it to a different system that has access to the internet, and you run this, you execute the symcheck, but you say /im, all right, to go ahead and ingest and read that manifest file, and then you specify the symbol server. Okay, a lot of times what I like to do is I like to give it the name of a local folder, like C symbols or whatever, as a nice local location for some of the symbols to be stored. I don't want to go fetch everything all the time from the symbol server, because a lot of times it can really eat up some of your research time. All right, your time is very valuable. Don't want to be downloading symbols from the server for forever. All right, so that's how you could do that for like one particular image or something like that. But what if you want all the things? What if you want all the symbols for all executables, Windows executables, right? Not custom ones. All executables and all DLLs. How do you do that? Okay, so one of the things that you can do is you can use a couple of binaries called SymStore and SymCheck. Okay, so SymStore, again, you have to take these over to the Debugging. Okay, so you'd have to transfer these to that other VM, that's your target. And there are some DLLs that need to be transferred over there too. All right, so debug help, debug engine, SymServe, and symbol check. Those DLLs should be over on that target VM as well. Okay, so once everything's over there, you say SymStore, right? We're going to add some entries to the symbol store. We're going to be recursive, and the folder path would be like C Windows and then a splat.dll. To basically say, go ahead and look at the C Windows folder, find me every single DLL file that's there, and we're basically going to go ahead and pull down all of those symbols for all of those DLLs. Okay, the actual process of that doesn't take off until symcheck is ran. Okay, then we'll go ahead and pull them all down. You can do the same thing for executables, right? Add to the symbol store all the entries for all the executables inside of C Windows, and then run symcheck against them and pull everything down from the Microsoft symbol server. All right, pretty nice to have. Now, it will definitely eat up some space. A lot of these symbols can be very, 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 very large. So if you have several air-gapped systems or whatever, it could be beneficial to have a separate system or a shared file, shared folder system or whatever for housing all of these symbols. I think one time when I did this against a Windows 10 image for all DLLs and all executables, I think that symbol folder was about 500 gigs, something like that, right? Just for one system. Imagine doing that for like 10, 20 systems that are offline, right? So where else can you get some information about like kernel structures and stuff like that outside of WinDebug? Virgilius. Virgilius is an amazing project that's out there online, virgiliusproject.com, and it gives you the ability to go ahead and explore various versions of Windows kernel for like 32-bit, 64-bit, different builds and stuff like that. So it's a really cool resource. React OS is out there as well as Geoff Chappell's resource too. Okay, sweet. Any questions so far? I think we're good. Yep, all good. All right, so that kind of takes care of the whole kernel piece of the poster. So flipping on over to the other side of the poster to like the Windows dev knowledge. All right, now here's what's really cool about these intrinsic functions. The intrinsic functions are internal to the CPU/compiler. And for like AMD and Intel, online, there is a really good resource that will list thousands of different intrinsic functions that the chipset or chip maker supports. So you can do things like encryption, decryption, any kind of mathematical operation, string comparison, comparisons of bits, flags, flipping things from like flipping the endianness of bytes. That's all available. There's so much to take a look at. So I picked 3 examples that I use probably more often for developing some implants that can help me with creating shellcode. Shellcode is very, very handy. And one of the things that shellcode has to maintain is its position independence. All right, it has to be independent of its position because you really can't guarantee and predict where it's going to be mapped into memory when you inject it somewhere. And intrinsic functions are position independent by nature. They are internally known, and the compiler will know how to generate the most optimized, I'll call it shellcode, the most optimized bytes or opcodes for that particular piece. And they're 100% position independent, and which is great when you're using like Visual Studio or something like that, and you're trying to build out a binary, like an executable or a DLL, that you need to go ahead and be pick. All right, you need to pick binary. So you can go ahead and extract all the bytes from the text section. Intrinsic functions really help you do that. They really leverage that. Okay. Now they're not portable across like ARM or x86 and stuff like that. So it's kind of specific to the architecture, but that's fine, right? Not a huge deal. All right. So you have a hasher routine. I give an example of how to do like an intrinsic hasher, Unicode string compare operation, and an intrinsic XOR operation. Okay. So I'm going to flip over. I'll go ahead and detach and let that go. Okay, and then I have a Visual Studio project or solution that's kind of ready to rock and roll. And for anybody who has seen the Intro to C series in its entirety, one of the parts, part 9 or part 10, I think it was, I went over in detail intrinsic functions and more of the beauty behind them. But since we're limited on time, I'll go over this a little bit quicker here. Okay, this example here, just doing a hashing routine that takes in a pointer to a Unicode string. Okay, here's why this could be of value. Imagine you're an implant developer, malware developer, or whatever, and you're trying to craft some shellcode. You're trying to figure out how in the world to find a function like load library, get proc address, or anything like that. You're not going to know where those functions are, right? Because you don't know where NTDLL or kernel base. You don't know where kernel base has been loaded. So you're going to find it. One of the first things you have to do is find the pointer to the process environment block. Once you find the PEB, you can then find the loader, the PEB loader, and then you can start to parse one of the 3 linked lists that keep track of all the DLLs that have been loaded in that process. And so one of the things that we'd like to do, that I'd like to do, is I like to make like a 4-byte hash of some of the names of the DLLs and functions, right? The reason why I like to do that and why many people like to do that is because we avoid strings. We don't want strings to be present inside of our implant binary or whatever to make it easier for an analyst to kind of get a sense of what we're trying to do. All right, so we use hashes instead. So what's happening here is I've included the proper header files, right? We almost always need the Windows header file. And then specifically, we're adding in some compiler intrinsic header files. Intrin, AMintrin, and mintrin, basically for like AMD and Intel support. And then these other ones, some of these other ones are just here for some C++ specific things to basically display stuff out to a terminal and stuff like that. You really can't use some of this stuff if you want this binary to be position independent. All right, I'll talk about that a little bit more detailed here in a second. So what happens is this intrinsic hasher will go ahead and be given the address of a Unicode string. And then we basically come in here and start calling some intrinsic functions like this one, the set0, SI128. What's great about these is the efficiency of them. They can operate on 128 bits at a time, right? Hence the number 128 at the end. Okay, so basically what's happening there is we're going to go ahead and zeroize or zero initialize this particular variable. All right, we'll go ahead and set 0, set this all to 0, make sure there's no junk or garbage data inside of it. Okay, so we go ahead and zeroize that. We'll get the length ready to rock and roll. That way we can go ahead and use that as our loop. All right, that'll be our breaking condition. And inside this loop here, what we're going to be doing is 8 bytes at a time. We'll go ahead and process values from that Unicode string. All right, and it has to be 8 bytes at a time because that's how some of these intrinsic functions are operating behind the scenes. And that's why it's so efficient and so fast. And you can operate on like 2 bytes at a time, 4 bytes at a time, 8 bytes at a time, stuff like that. Okay, so that's what we're doing here, operating 8 bytes at a time inside the string. And we'll go ahead and at this particular iteration, all right, so like iteration 0, we'll go ahead and come into the buffer and pull out 8 bytes. All right, so like 8 letters, if you will, 8 characters. We'll go ahead and take that, and we will load that into this variable here, all right, this current chunk of 8 bytes. Then what we do with that current 8-byte chunk is we'll call an XOR intrinsic function. And then we'll go ahead and say, I want you to XOR this current chunk against this hash. And then we'll go ahead and update the hash variable. Okay, cool. So that loop will go ahead and continue until it processes practically everything of this Unicode string. But when we're getting ready to be done with this and before it returns, not every string value is going to be evenly divisible by 8. Right? There will be some leftover chunks that we'll have to deal with in just a minute. So I'll talk about that here in a second. But the parts that we do have, the parts that are ready to go ahead and finalize, we go ahead and call store. We go ahead and call the store intrinsic function. Okay, we'll go ahead and say, hey, the current hash, right? We'll take this hash value and shove it into DW parts, right? So that's going to basically be our final hash here. DW parts, when that is all said and done, ready to rock and roll, we're basically going to come in and access each little part and, in other words, flatten it, right? That's what everything is doing here. We're flattening everything, kind of like a scalar operation, if you will. Flatten this all down and shove it in a double word value. Okay, so we're going from a 128 bits down to our little double word. Now this leftover business I talked about, when something isn't evenly divisible by 8. The leftovers. This loop right here will handle all of those straggling bits, right? The leftovers. This is going to do a 1-for-1 hash, right? 1 byte at a time until everything is completely hashed or XORed. Now, when it's all said and done, we can go ahead and return DW hash, 4-byte hash, back to whoever called it. Okay. Now, this function right here, all this is a position-independent function, right? A lot of times I've heard the word PIF, right? Position independent function. What that means is this function here doesn't rely on anything external. We're not calling any Windows APIs or anything like that. Nothing whatsoever. So you could come in and extract the opcodes for this one, and you would have position-independent shellcode. Now, inside main is definitely not position-independent whatsoever. What we have here is kernel base, kernel 32, and ntdll. These are all going to be treated as Unicode strings. And we're just going to go ahead and basically initialize these into their own variables. And then we'll call the intrinsic hasher on all of them. And then we'll spit it out, right? And just spit everything out to using wcout. And away we go. And then just for some extra verbose details, if some of these data types are kind of like foreign or unknown to you, I'll go ahead and print out the size of each of these data types to kind of show you how many bytes we're working with, how many bytes they can hold as we go through the motions. All right, so I'm going to hit F5. Go ahead and run this. And there we go. There's the results. Okay, so the hash of kernel base is this value here, and we see kernel 32 and ntdll. And then the size of a uint32 type is 4 bytes. Size of double word is also 4 bytes. And then for the intrinsic piece specifically, the M128, all right, the full width of that was 16. All right, so we got 4, 4, and 16. Now, what can you do with these? All right, now you have the hash. Cool. What can you do with the hash to help your implant, or help your shellcode rather, find kernel base? Okay, so let me see here. Okay, so this function here, this entire program actually, is 100% pick. So when this builds, the resulting executable is pick. So you can go ahead and extract the opcodes from the text section, and you could treat that as a shellcode. Okay, so you have the hash of something, right? Like kernel base. You call it intrinsic hasher, boom, boom, done, right? I showed you that on the other project. It's the exact same code. Okay, so you go ahead and you use another intrinsic function. Read GS keyword, very specific for 64-bit. And what it's going to do is going to grab a keyword value from the GS extended segment register. Now, what specifically are we grabbing here? We use a field offset macro to say, hey, within the TEB, the thread environment block, go down, find out where the process environment block field is located, and find the offset, right? So from the start of the structure down to process environment block, figure out how far away that distance is. Calculate that. And whatever that value is, we'll pass that as an argument to read GS keyword. And just grab that value, right? Grab that keyword value. And that is going to be the pointer to the process environment block, right? The PEB pointer. We'll do a little check to make sure we actually have something. All right, and then what we can do is we can go ahead and start to process the loaded modules that should be present inside PEB loader. So we'll come in and use the arrow notation, go ahead and grab loader data, pointer to it rather. And then we can go ahead and grab one of the 3 doubly linked lists. All right, now Windows internally is using a circular doubly linked list. So we have to make sure that the head of the list, if we see that come up twice, we know we're done, all right? And there's no end marker really that says, hey, you're at the end of this list. Okay, so we'll go ahead and we'll say the in-memory order of all the modules that have been loaded in this process. We'll go ahead and grab the list head for that. And we'll go ahead and say, you know what? I want you to find every single entry inside of that. And I'll go ahead and make a hash. I'll make a 4-byte hash of every single DLL that has been loaded. And I'm going to do a little check. I'm going to see if the current hash is equal to the hash that I provided, or in this instance, the hash of kernel base.dll. So as you go through the motions, everything will be compared. And if we're good, if we have a match, Then we'll go ahead and say, hey, you know what? I'm interested in that particular one. I want to know the base address of that module. Okay, and then you can do a little check, and then you can start to process the goods. Okay, so the goods could be walking the export address table, trying to figure out where a particular exported function is located. Okay, that's some of the stuff that is very, very valuable for implant developers or shellcode authors and developers, is being able to go through and do all of this in shellcode. Okay, so cool. Let me flip back to the poster real quick. Okay, yep, functional hooking, okay, for 32-bit, 64-bit, some decent differences between those two. One of the things to keep in mind if you're trying to implement your own hooking is padding. All right, a lot of times what you have to do is make sure the padding and the alignment is still good, so you can add some nops in there or some int3s. I've seen people use both. All right, and then on the right-hand side, we have system call stubs. Okay, let me scroll over a little bit more. Sweet. System call stubs. You have ones that'll be specific to like GUI threads and others to like non-GUI threads. All right, so a lot of times you'll see people talk about NTDLL and that particular module and all the system calls that are present there. So one of the things that you can do is you can take a look at NTDLL and look at the system call stubs and kind of get a sense of what a system call stub looks like, right? The signature of a sys call stub. All right, so we have NT-access check as a demo, right? Just picking one. One of the things that you have is the actual number for that particular system call, or the ID of that system call, right? 0 is the first one. And there's a lot of them inside of NTDLL. Okay, all right, so that's the first one. But one of the things that is very, very annoying, I would say, for implant developers or whatever, is when a function is hooked, when a system call is hooked, you no longer have access to see this value. All right, so this one's hooked. It's gone. All right, it's been overwritten, and we still have some padding bytes here, but instead we have this jump. Right, this jump is probably going to go to some EDR products, DLL, that's going to do a bunch of things. Maybe it's going to send some kind of packet or whatever to its kernel mode component to do some processing, maybe send some stuff to the cloud as well for more processing. Who knows, right? It's all proprietary stuff. All right, so in essence, how in the world could I still find out what the system call number is for NT-access check or anything else? Right now, there are quite a few methods or techniques that are out there today that allow you to still dynamically retrieve system call numbers while maintaining your position independence, right? Which is crucial. Okay, because these system call numbers, they're not going to be the same across every version of Windows, right? Linux, pretty static, the complete opposite. You know that syscall number, you're good across many versions of Linux. Windows is never going to be that way. Okay, so that's what a hooked system call looks like. Okay, cool. I talked about some of these intrinsic functions before to grab a pointer to the PEB, stuff like that. There's a few other ones that could be of interest to you, like byte swap. Byte swap U short and U long. I give a little pseudocode example of how you could use those. Basically, it's a way to swap the endiness of a 2-byte value and a 4-byte value. Cool. All right. Well, that is a little quick walkthrough of the poster. We're a little bit early, 2 minutes early. Does anybody have any questions about anything? Feel free to type away. If you have any more detailed questions or if you want to see more detail about some of the stuff that I talked about in the poster, check out the Intro to C series, right? It's all free. It's out there on the SANS workshops. The current one we got going on right now is Intro to WinDebug or Intro to WinDBG. And in a few weeks, I believe towards the end of this month, we'll have part 2 of Intro to WinDebug, and we'll be talking about time travel debugging. I am not the person that can answer that question. I teach. I don't control any of that. But I try to put out as much free content as possible with workshops and stuff like that and webinars. But it is nice to have employers to help out with that as well. There's also a work study program that's available. And in fact, that's how I got started. That's how I took my first CNS class, actually, was through the work study program. A lot better that way. Cool. Does anybody else have any questions? All right, sweet. Thank you all for attending the walkthrough of my poster. If you want, again, another plug, if you want to see more details at length, check out some of those resources I gave you. All right, y'all, have a good one. Thanks for tuning in. See you next time.